Hello everyone, this is the second lecture on the conservation laws and we are addressing momentum balance. Now momentum balance is pretty much like second law of Newton, which is F is equal to ma. We write it for fluid flow, and especially we focus on the momentum balance conservation for free flow for any stream of fluid, and then also address at the end what do we use usually in porous media systems, which is just Darcy law. The Darcy's law will be used as replacement of the momentum balance at the continuum scale, at the reservoir continuum scale, where we can actually define permeability effective. If we do pore-scale simulation in porous media, we use Navier-Stokes or Stokes law, which is pretty much the same as I'm going to explain now. So let's get it started. Starting from the last lecture also, we are observing a stream of flow, and Lagrangian way of a conserved quantity like X is total change over time of my conserved quantity, which is per mass, will be X, so it needs to be multiplied by the density and the volume of my system. That's the total change of my conserved quantity in Lagrangian system. That is equal to change over time at a fixed control volume that Eulerian system uses, and that is a fixed control volume, and we call the volume of it as omega and boundary of it as partial omega. So in the Lagrangian system, it will be ddt at a fixed location of rho x dv plus flux across the boundary of my control volume of rho x, and then the flux, which is u dot n ds, the surface. And n is the normal vector outward of my surface, and naturally u dot n for a stream of flow, the outgoing velocity will be positive because they are parallel to n, and incoming fluxes are negative because they are in the opposite direction to n. And u velocity has two projections, normal and parallel to the boundary of control volume. We are caring about only normal one, that's why u dot n is written. So it's projection only at the normal. The other one, which is rotating at the surface, is not leaving the boundary, so it will not cause change of the conserved quantity x. So that's Reynolds transport theorem. And for momentum, x, which is the conserved quantity per mass, intensive value will be, momentum is mv. If you remember, per mass will be velocity only, so it will be u. If you write it based on x prime, which is per volume, x prime, which is per volume, your x prime is rho x, which will be rho u. So depending on what you will need, per volume or per mass, that would be the same. The equation is actually pretty much u. So I'm going to write the change over time of the total momentum that I have will be change over time at the fixed location of my control volume, which is the Eulerian system, which is rho u dv plus flux of momentum at the boundary of rho u, then u dot n ds. So this is my expanded way of Eulerian way of the total change of momentum. What we know from second law of Newton's second law of motion, is that the summation of forces is equal to the ma, the change over time of momentum, right? So I need to see what are the acting forces on my fluid particle now, because this is the change of the momentum. And that is, two sources of forces we are considering in this course. One is the body force, gravitational acceleration. That's the body, that's the mass, the weight of this system. So it's G, and that becomes integral of rho G d volume. That's volume forces, body forces. The surface forces acting on a particle of the fluid are related to the quantity that we call it as a stress, right? They are stresses acting on the surface of the fluid particle. So I am going to have at the interfaces all the stresses acting on my fluid at the surface ds. That's what matters for me. All the surface forces. Based on Cauchy stress theorem, the stress acting at the surface can be written as projection of the total stress tensor to the normal direction of my surface. So this is integral over the boundary of the stress tensor projected at the normal of the face, the boundary interface. And that's Cauchy stress theorem. And so you see that it's like a stress integration at the surface. I can use now divergence theorem, and that divergence theorem says you can do this calculation of a stress at the interfaces by simply going through the volumetric integration of divergence of a stress at the volume. Because the stress n ds is like flux and like the net outward forces or stresses at the boundary, at the interfaces of your fluid particle, and I can simply use divergence theorem to make it divergence of stresses. So in that sense, I can also use divergence theorem here and make the flux of the momentum to look as the integral over the volume divergence of rho u. That's the d volume. And so I can clean it all up and then write one equation in which then the integration of dv is everywhere. The first term here is d dt of rho u d volume plus integration over the volume divergence of rho u dv. That's equal integration of rho g dv plus integration of divergence of stress dv. Now this term I can get rid of integration over volume, because pretty much like the last time, when integration over any volume is balanced, it must be the whole term should balance. So I can bring the right hand side to the left hand side and say the entire summation integration is zero, therefore the term needs to be zero, and then eventually I get the equation that I like to have, which is actually getting rid of the integral forms, and eventually therefore I get to know that this is d dt of rho u plus divergence rho u. I can write a divergence rho u, that's fine. I can also, it's very common to write it rho and then u dot nabla operator times u. That's much more intuitive, and you will learn soon why. That's the very same mathematically as the other one. Is equal rho g in a vectorial way. If you're writing in x direction, g is 0. If you're writing in z direction, g has a value, so you consider that. So that's a vector plus divergence of a stress. Fantastic. This is the most basic elementary way of writing force balance and momentum balance for a fluid stream. Now, I am basically done except the fact that I need to introduce you what is that stress tensor. What's the divergence of a stress? So what are the stresses acting on fluid? So, the total stress acting on my fluid can be decomposed into the average trace of them, which is then the thermodynamic pressure minus Pi. If the stress is positive in tensile force, then P is compressive force, so that's the negative sign, and plus all the other terms that pressure does not account for. Now, if it's an incompressible flow that is shear, deviatoric ones. But in general, tau is whatever pressure does not take care of, which is 1/3 of the trace of the stress tensor will remain in the deviatoric part. Now, I can measure P. I know pressure, thermodynamic pressure. It's quite clear. I do not know tau yet. So I need constitutive law to relate tau with something I understand, and that's the science of rheology. So tau can be written as viscosity, the shear viscosity, times gradient of u plus gradient transpose of u plus lambda divergence of u identity matrix. This is the shear viscosity mu. Lambda is the second viscosity. Now, this way is very neat and clean. I see gradients here and I see divergence u, which is the volumetric strain, it's the compressibility. However, if I write it this way, physics way, looking at it, the first term is not purely shear. The diagonal entry of the first term still is non-zero. To make it purely shear plus purely compressibility, I am going to introduce bulk viscosity. Bulk viscosity as a complementary coefficient to the shear viscosity. That K is defined as lambda plus 2/3 of mu. And therefore, I can rewrite this equation and say that based on this, my tau is mu gradient u plus gradient transpose u minus 2/3 of divergence ui plus, then I have k divergence u identity matrix. This way of writing tau, which is the remainder, the effective one, if this is the total stress and this is the pore pressure part, this is the effective one left. Whatever stresses that pressure is not taken care of, that will be decomposed into the first term, which is purely shear, and this is the bulk compressibility. So that will be the compressibility part, which is the K bulk viscosity is being considered for. Which means, in a way, that when you change the volume of your fluid, there is an associated viscosity to it, and that's K. Now, if I assume that my system is incompressible, this means divergence of u is 0, and therefore I can neglect these two terms and eventually write my tau as mu grad u plus grad transpose u. Fantastic! Because now I can go back to my Navier-Stokes. It's not yet Navier-Stokes, it is just force balance. And say the term will be d dt of rho u plus rho, and this term is u nabla. You will see what u nabla is. I can just write it for you soon. I will write it very quickly. It's very simple. And that is rho g plus divergence of stress will be the divergence of minus pi, which will be then minus gradient of pressure. And then I have plus divergence of tau, which will be plus divergence of tau in the term of incompressible tau. That will be mu grad u plus grad tu. This term is mu Laplacian of u. Divergence of gradient is Laplacian. Divergence of gradient transpose is 0. You can translate it to gradient of divergence of u, which will be 0. So this is it. For linear relationship between tau and viscosity, which is for Newtonian fluids, which have constant viscosity and relationship between tau and grad u is linear, then we get this beautiful equation that now can be written in any coordination system that you have, like for Cartesian system or radial system. For example, for Cartesian system of x, y, and z, x momentum is what? d dt. I can bring rho out because it's incompressible, so rho is constant, so give me this possibility to put rho d dt of u, that is ux, right? So I write ux here, because I'm writing it for x momentum balance, plus rho. Now, u dot nabla, what does it do, my friends? It's the flux of momentum. So that becomes ux nabla x, uy nabla y, uz nabla z, which is ux d dx plus uy d dy plus uz d dz. And then since I'm writing it for x momentum, I write ux for all of them. That's this u. U dot nabla will be ux dx, uy d dy, uz d dz. And then it is equal rho gx. If I have gx, then I write it. If not, then it is 0. So I assume I don't have, or maybe I have, so I write gx if I have in x direction gravitational thing, depending on how I define x and y and z. Then I have dp dx. Then I have plus mu Laplacian of u. What is Laplacian of u? It is d second dx2 plus d dy2 plus d dz2. And since I'm writing it for x force balance, x momentum balance, I write ux in all denominators here. When I write it for uy, I write it rho d dt of uy, rho dux dx, uy, but the y terms here stay the same. So I can write it for uy by just replacing ux's in the denominators by uy. All the terms and derivatives will stay similar. This is when we do in Cartesian coordination. I can do it in r and theta. I can write it in r and theta and z, or r and z, which is radial or cylindrical coordinate. You just need to look up to any fluid mechanics textbook. In my generation, we used to read textbooks, fluid mechanics. Now, I guess you Google or you use AI toolboxes, etc. that you have. But you see what is the operator gradient and divergence and these terms in your coordinate system. So you will write them based on that coordinate system. The beauty of the operator's divergence gradient is you can write them for all different coordination. If I write it only x, y, z, then I need to write again for r, theta, etc. But when I write it gradient and divergence operator, I am actually pretty much generic. Now, this is for free flow. Free flow. When I do porous medium, at the continuum scale, I use Darcy's law. Which says U is minus K over viscosity gradient of pressure, if there is no gravity. If there is gravity, it will be also rho G as well, rho G, right? So it will be potential gradient. The thing is, the average Darcy velocity is proportional to the pressure gradient here, if I do fluid flow in porous media in an effective way. If I do pore-scale simulation, though, there I use Navier-Stokes or Stokes flow, because flow is very, very slow. So viscous forces dominate. So these forces dominate compared to the momentum forces. So Darcy's law is used in porous media as the replacement of momentum balance in the continuum scale representations. For fluid dynamics in general, we do it Navier-Stokes, which is exactly what I just wrote down for you here. One catch at the end for those who are watching at the end, also for you all, is that whatever I wrote was for single phase flow. So I had one density, one fluid in the system. Now, when I move on to multi-phase flow systems, you will see that the space will be occupied partly by phase 1 and partly by phase 2. And the interactions of those phases matter a lot as well. So that's all about momentum balance for fluid dynamics, which ends up to be the Navier-Stokes by relationship of the tau and the pressure, total stress will be there, and so we get it to the Newtonian fluids where we have shear part, or not shear, the non-pressure part represented as linearly by the gradient of the velocity of the fluid with the linear viscosity, constant viscosity, and that's a linear function, and that's Newtonian fluid. Non-Newtonian fluids will have non-linear relationship between their tau and their gradient of velocity. Viscosity can have power law way. It can be shear thinning, it can be shear thickening, it can be viscoelastic, it can have a lot of complex behavior. As I said, the science of it is called rheology. So if you search rheology, you will see all the great work of a lot of scientists on identification of the relationship between tau and gradient velocity for specific fluids like dough, like paint, toothpaste. Blood also, blood is non-Newtonian. Blood is not Newtonian, it's non-Newtonian. So I hope you enjoyed this, and we move on to energy balance.